Welcome to the video on z-scores. And so let me get us a definition up here on the board. So z-score. So what is a z-score? I mean, the way I like to think of a z-score is just the number of standard deviations the raw score in your data set, or any raw score you could say, is above positive or below negative the mean. So basically what you want to know is your raw score above? If it's above, it's going to have a positive z-score. And if it's below the mean, your raw score, it's going to have a negative z-score. So I've brought back the data set that we had used in some of our prior videos just to be consistent, where I is just our index of how many faculty members that we looked at, and X sub I is the number of years of employment. Okay, and if you remember from this particular data set, our mean, I'll just write it down here at the bottom, our mean of this data set was 6, and our standard deviation, denoted by S, was 2.71. So if you need to review how you come up with the mean of 6 here, or the variance, or even how we get standard deviation, I would suggest you stop now and go back and look at those particular videos. So let me just kind of start by throwing out the formula. So to go from a raw score to a z-score, we're going to use the following formula. Let me get that underlined. You're going to use z to get any ith z-score will be the raw score x, and I'm going to write this in population parameters first and then explain why we will kind of modify this. So take the raw score minus the population mean, that's what mu equals here, and then divide by the population parameter sigma, which is standard deviation. Okay, here's the trick here is we don't know what these population parameters are, and so mu for us, which is the population mean, our best estimate, point estimate of that is going to be the sample mean, so we'll replace that with the sample mean, and our best point estimate for the population standard deviation will actually be the sample standard deviation, which would be S. And so this formula then will become x minus x bar divided by S. And so what does that mean for us? So let's just pick one of these. Let's just pick, I'll circle it here, let's just say that me, Dr. Gould, is case I equals 8. And so my raw score for the number of years that I've been employed at Southern Miss is 9. So let's calculate, given what we know down here with the estimates, what this would be. So let's just kind of plug and chug. So my z-score then would be z equals 9, number of years of employed, minus the sample mean, this piece down here, this 6, so 9 minus 6, divided by the standard deviation for this particular group of observations, which was 2.71. And so if you kind of just plug and chug these numbers, you should get positive 1.11. Now why is it positive? Because my raw score, and I'll just circle in red here, my raw score 9 was greater than the mean here of 6. Okay, so it's going to give me a positive integer in the numerator when divided by the standard deviation, will give me a positive z-score. I want you to keep in mind here that in this equation over here, this would be 9 years minus 6 years. Okay, so I just years, 6 years, and 2.71 standard deviation is in years. So what's going to happen is these units of years will cancel out, and the z-score in and of itself becomes then unitless. Okay, it becomes a unitless measure of your distance, that raw score's distance above or below the mean. Well, and the neat thing about this then is that you can then graph your z-scores in a histogram, or you can just graph them individually. And so let's look at what that might kind of be for us. So if we had, let me try to get a little baby normal curve up on here. Let's try to get a little bit better normal curve than that. Okay, so if this is our normal curve, and we know that the middle point would be a standardized score of 0, which would be equal to the mean, right? So if you had a score of 6 here, let me do this in, we'll do it in pink. If I had a score of 6 here, raw score minus a mean of 6, that would give me a 0. I was right at the mean, okay? So this 0 right here is also equal to the mean, or the x bar, or the mu. And so then if I put in my +1, +2, +3, -1 standard deviation, -2 standard deviations, -3 standard deviations, just a rough sketch. Well, let me take out this piece here just for a second, just to make things a little bit clearer for us. Let me cut that out. If you looked at the mean, if we were just going to put our raw scores in on this curve, not our standardized scores, that would be 6. Well, at 1 standard deviation, if you added 2.71, this 2.71 down here, I'm going to take that back off, this 2.71 down here, then a raw score of 8.71 would be equal to 1 standard deviation. If you had another 2.71 onto this at 2 standard deviations, you'd be at 11.42. If you took 2.71 and subtracted it from 6, then you'd be at 3.29. And again, if you took another 2.71 away from this, that would be 0.58. And so that's how your raw scores would graph. But let's look at the standardized score. So our score of a 9 yielded us, when we normalized it by the standard deviation, that's what we're doing here, normalizing by the standard deviation, it gave us a z-score of positive 1.11. So essentially that raw score of a 9 would fall, well, let's just say that this is 1.1 right here, 1.11. So that's our raw score would actually graph there. Well, let's say that we want to move backwards. We want to calculate a raw score from a z-score. So let's go through that exercise. So we're going from raw score to z-score. So now we want to go z-score to raw score. So we want to solve for raw score. So we want to get an x, and that x, if you just do the quick algebra and move these terms around, is just going to be the z-score multiplied by the standard deviation. Add to that the actual mean or x bar. Okay, so again, pretty standard here. So if we took our x, plug and chug these numbers here, the z-score, again, we're still operating off of this 9 here, and you put 1.11 in, and you multiply it by the standard deviation of 2.71, and then you add to that the mean of this, which was 6, then what you would pop back out then is a raw score of 9. And so you can go back and forth. You can calculate from a raw to a z, a z to raw to z, just back and forth. Remember, the raw score is an observed score that's in its original units, and the z-score is a standardized score that is unitless. Again, these units will cross out, and that is useful to us, having something that's unitless, because if I said to you, Gould has been here 9 years, and that is just in its raw units, we don't know if that's more or less than the average, and to what extent. How far past average is it? And so the nice thing about the z-score is it gives you kind of a sense of how far beyond the mean you really are. So if I reworded that and I said to you, Gould's z-score for the years of employment that he's been employed at the University of Southern Mississippi was 1.11, then it's certainly not necessarily an unusual amount of time, because if you go back to the number of scores, we kind of consider something unusual. Let me scroll that back down again. We consider something kind of unusual if it goes beyond this plus or minus 2 standard deviations, which is again about, well, actually it's 1.96, gives us 95%, but kind of within this band, whether you're at 1.96, negative 1.96, or positive 1.96, whoops, wrote that one in the wrong spot, or positive 1.96, you're about at 95%. So going on beyond this 2 standard deviations, so if I had been here 20 years, okay, what would that relative to this this data set? So if we took 20 minus 6, it'd be 14, and then 14 divided by the 2.71 would have given me a standard deviation, or a z-score of somewhere around 5, a little over 5. That would be, 4 would be out here, 5 would be way out here. Certainly that would be something very extreme. You would only see it less than a 0.1%, of the time. And so we don't really consider something kind of an abnormal or extreme score until it kind of goes beyond this 95% kind of barrier. And so certainly 9, a raw score of 9 falling in at a z-score of 1.11 is certainly within that 95% kind of barrier. And so we wouldn't consider that an unusual or extreme score. So that's one thing that it does for us. It gives us kind of this unitless way of looking at distance. The other reason that it's important to us is it allows direct comparisons. You can take 2 completely different variables. I could take years like this, because the units cancel out, and I could plot something. I could plot a z-score, and then I could take a z-score on vertical height or jump or something that was in inches or yards or feet, and get z-scores, and then you can compare z-score to z-score. And it allows you, because it's unitless, to make comparisons. I could take my age and or the amount of years that I have been employed in my z-score and compare it to your z-score on vertical jump in inches. If we wanted to make some kind of comparison there, you could do that because it is, again, unitless. So it just affords us a really nice, clean way of making those types of comparisons. So the take-home message is here in this particular module or video is just to look at how you go from a raw score to a z-score, how you go from a z-score to a raw score, how you would kind of plot them on the normal curve. And what we need to build onto this then is the concept of what a t-score is, and then moving on from there, we need to look at area under this curve, as that will be a useful piece of information for us as well. So until then, thanks for watching the video.